So let's go back to basics and remember what orbitals are, okay? These orbitals are places where we're likely to find an electron. Now, where do we get the orbitals from? We get them from wave functions. All right, the wave function is a mathematical equation that describes the motion of an electron around an atom. All right, it's more complicated than that, but that's where they come from. And the origin of the wave function comes from treating the electron like a wave, which is already weird. Okay, let's go back in time to 221. We looked at the photon, which is a particle of light. We treated light, which is normally a wave, as a particle. And then we did the opposite. Well, we took an electron, which is a particle, and treated it like a wave. And that's what we're doing. That's what quantum mechanics is all about. We're blending this boundary between matter and wave, matter and light. So we're treating the electron like a wave. Now this is a three-dimensional wave because it's a volume of space. That's where we find the electron. That's too complicated. Let's simplify even further. Let's go back to one-dimensional waves. And let's remember what a one-dimensional wave looks like. It looks like that. And it has phases, right? So the wave goes up and down, up and down. These phases, they're labeled positive and negative phases, but they have nothing to do with charges. They're not a charge. It's not a positive charge like a proton's charge. It's just a label for the direction of the phase. And so if a wave has phases, well, an orbital will have a phase too, because an orbital is a wave. So this is the orbital kind of description of, in one dimension of a 1s orbital. So here's what we think of when we think of a 1s orbital. If I just take a slice of that, this is the wave function of that. It's showing a large electron density close to the center of the atom, and the density drops off as you get farther away. Well, this is just one phase. You could draw the opposite phase version of the same orbital, and it would look the same. It would work the same way. It would just be the opposite phase. P orbitals, we never actually worried about the phase before, but we know the shape of P orbitals. They are these dumbbell-looking orbitals. They have 0 electron density at the center. But the phases are actually the opposite. The two lobes actually have opposite phase. So sometimes you'll see them written as a plus and minus. Not charge, it's just the two different phases. And this is kind of a representation of that. So one side is the positive phase, the other side is the negative phase. Okay. So given that orbitals have phases, what does this do for us? Well, remember what phases of waves do. When I have two waves that interact with each other, overlap, if they're in phase, meaning if the two peaks overlap and the two troughs overlap at the right place, they will do something called constructive interference. They'll combine together and make a wave that has double the amplitude. And if I take two waves that have opposite phase, so here's the positive phase, here's the negative phase, they overlap, they will destructively interfere. Well, that's what's going to happen with our orbitals. When I take the orbital of one atom and overlap it with the orbital of another atom to make a bond, they can do both of these things. They can constructively interfere and they can destructively interfere. So here are two s orbitals from two different atoms. That's the shape of one s orbital. It's kind of this mound, and there's another s orbital here. Notice where they overlap. If they're in phase, they will constructively interfere and make this region here where it's double. But if they're out of phase, and so these are the originals, the dotted line part, when they're out of phase, they will destructively interfere, and the red line here is what happens. They will make a region of 0 electron density between the two atoms. All right, so that's the destructive interference. So they cancel the electron density, which is the opposite of a bond, right? In a bond, the two atoms need to be able to share electrons between them. This is doing the opposite of that. So what happens is you create, when you mix two atomic orbitals, in this case, if I take a 1s from one hydrogen and the 1s from another hydrogen atom, those two atomic orbitals will mix together in two ways. they'll either constructively interfere and make what's known as a bonding molecular orbital, because now they've combined together, it's an orbital for the molecule, or they'll destructively interfere and they will make an anti-bonding molecular orbital. Now this sigma here, this is the Greek letter sigma, this is describing, we've learned this in 221, this is describing the type of overlap the orbitals do. If it's an end-to-end overlap, where they overlap in just one spot and that's it, that's a sigma bond. So when you overlap two atomic orbitals, you will get two molecular orbitals. In this case, one of them is going to be bonding, the other one's going to be anti-bonding. We label the anti-bonding MO with a star. Usually they'll almost always have a star on them. And then subscript here is optional. You don't have to write this, but this subscript just kind of informs you what atomic orbitals that new molecular orbital came from. The big thing, the takeaway, and I'll repeat this at the end, is the law of conservation of orbitals. If I combine two atomic orbitals, I will get two molecular orbitals out. Okay, so far, you okay? Yeah.
So just to be clear, molecular orbital is when it's between two atoms, and an atomic orbital is when it's by itself.
Well, no, so sort of. An atomic orbital comes from the atom. Just that's what the atom came with. A molecular orbital is what you get when you combine atomic orbitals from multiple atoms. So it's two or more atoms make molecular orbitals together. Yeah.
Following up on that, so anti-bonding, could we say anti-bonding is when they stay more on one atom or the other versus bonding, which is more between, or like hang out, so to speak?
Sort of. I'm trying to think.
Also, these are like
what I would think of these, and maybe it'll get clear later, I would think of these as states where of ways you can describe what's happening with electrons. So if electrons are occupying this molecular orbital, then they are being shared. If electrons are occupying this molecular orbital, then they're doing the opposite of it. They're doing what's called an antibond. I don't know if there's a good visual for it, because this is quantum mechanics. This is one of those things where it's math, really, and not something that our brains are intended to comprehend. So this is all based on math, FYI, and you don't have to know any of the math. It's an advanced class, but you probably will take it eventually if you're going to do any kind of science. This is linear algebra. This is based on linear algebra. So if you understand, linear algebra is a weird math class because you're doing weird things with equations. You're like, why am I doing this? Well, this is why. We use it. So this is just another visual of the same slide from before. Remember that these orbitals, these spheres, is an artist's representation of where you might find an electron. There's no real cutoff. It's just, hey, the artist can't draw feathery edges like that. This is really what an orbital might look like, although this is another representation. So the dots, where the dots are densest is where you're most likely to find the electron. Where the dots are less dense, you're less likely to find the electron. So you can see that there's a heavy density right between them, but in the antibond there is no density between them, so you don't find any electrons between them. This LCAO stands for linear combination of atomic orbitals. Don't worry about it. That's bad. Okay, sigma bonding, sigma antibonding. So let's see what they're good for. So this sounds really complicated, and it can be, although we're going to stick with the simpler forms. So we have, there we go, we have hydrogens, molecular orbital diagram here. And sometimes you'll see just the molecular orbitals. This is what you make when you put two hydrogen atoms together. Sometimes you'll see it drawn like this, where you have the original atomic orbitals. So these are the two hydrogens before they get merged into make a molecule. So there's an electron in this one, there's an electron in this one. And then when I make H2, I show, well, the atomic orbitals merge together to make these new molecular orbitals. And that's what you get. So this is, sometimes you can ignore this. This is what they originally were by themselves. This is what happens when you make the molecule. So how many electrons can each molecular orbital hold? Well, a molecular orbital is just like an atomic orbital. The rules apply the same for molecular orbitals as atomic orbitals. They each hold 2. 1 electron spin up, 1 electron spin down. Same thing. What is the capacity of the combined, and I'm going to use the word band here, but just think of it as, if I add up all of the new molecular orbitals I've made, what is the capacity for electrons for these molecular orbitals? How many? 4. I can hold 4 total electrons. I can put 2 here and 2 here. That's how many I could possibly fit. But for hydrogen, what capacity is filled? So this is where we take, okay, this hydrogen originally came with 1 electron. This hydrogen originally came with its own electron. So those 2 electrons are still there in hydrogen, the molecule, through hydrogen, 2 electrons, so they'll go here in the lowest energy molecular orbital possible. And that's it, just 2. So if it can hold 4 and there's only 2 in there, it is half filled. Yes?
So can that, I mean, I don't know, maybe you just drew it the way that you drew it, but can that one on the left or right there, can they switch their spin, the electrons?
Yeah, they can. I think you'll see other books that do 1 spin up, 1 spin down. They have to switch spin in order for them to fit like that. So yeah, they will switch. Yeah.
But they will just generally always switch spin.
Yeah, they'll rearrange an energy so that they will work. They'll be the lowest energy state possible. Yeah.
Cool.
Now, some of the things I did that I didn't really talk about. These molecular orbitals. The bonding molecular orbital is always lower in energy than the original atomic orbitals. So these 2 are the same because they're the same atom. But when I make the bonding MO, it's lower in energy. The anti-bonding MO is always higher in energy than the original atomic orbitals. Now, the distance between, the energy difference between these 2 is something we're going to look at later. But sometimes it's big, sometimes it's small. We'll look at that later. Yes?
Is it always like symmetric though about the
If they're the same atom, yeah, it's going to be symmetric.
like the conservation of energy kind of?
Yes. Yes. Yeah, it should be. Yeah. Yeah. Okay. So there's H2. And, this MO diagram, what is it good for? Well, there's a few things. One is bond order. I could find what the bond order between hydrogen in a hydrogen molecule is. And you might say, it's overkill. I already know it's 1 bond. I could do a Lewis structure for it. Yeah, well, that's true. This is definitely overkill for a simple molecule like hydrogen. So the bond order is number of bonding electrons. So there's 2 electrons in a bonding MO. Minus number of electrons in anti-bonding MOs, there's nothing in here, divided by 2, which you get 1. So single bond, that's what we figured out. Not a surprise. Another thing that you can get, and I did mention this in 221, is whether the molecule is paramagnetic or diamagnetic. Remember that? So paramagnetic is a substance that is attracted to magnetic fields. And you can tell something is paramagnetic if there are any unpaired electrons in it. So here's H2. I see no unpaired electrons. Everything's paired up. So H2 is diamagnetic. So diamagnetic is when it is not attracted to a magnetic field, slightly repelled actually. And so that's another thing MOs are good for, is for understanding whether you have a paramagnetic substance or a diamagnetic substance. I think in 221 we focused on atoms. being paramagnetic and diamagnetic. But now we can do molecules. And this will explain the difference between nitrogen N2, the liquid nitrogen being diamagnetic, and liquid oxygen being paramagnetic. I think I showed you guys the video, but I don't have time to show it right now, but we'll get to it. So, as the bond order increases, the strength of the bond will increase, okay? A double bond is stronger than a single bond, a triple bond is stronger than that. So that is not under question. But with this, we can actually get fractional bonds, and those are still bonds, but we can also get bond orders of 0 or less. So if you get a bond order of 0 or less than that, what that tells you is that you're not going to make a bond. It'll be nothing. Like two atoms will bump into each other, temporarily overlap their orbitals, make no bond, and so they'll fly apart again. Okay? So how do we see that? Well, let's do helium, and then let's do these weird variations here. And to do helium, I'm going to just cheat a little bit, and I'm going to relabel everything, because what does helium have? It has a 1s orbital, just like hydrogen. So helium's MO diagram looks exactly the same, except for the fact that helium comes with 2 electrons. So 2 here and 2 here. And so when I fill my molecular orbital diagram, okay, what happens if I make helium-2? Well, that's what the MO diagram would be. And I would have 1, 2, 3, 4. So 1, 2, 3, 4 electrons. And then when I do the bond order calculation, I would get 2 electrons in bonding MOs, 2 electrons in anti-bonding MOs. Divide by 2, 0 bond. That's not a surprise either. Okay, we know helium doesn't make bonds. The big, this is another B. This should be C. The big thing is for C. What about helium-2+? So helium-2+, what does that mean? Plus means you've lost an electron. 1 electron's gone. So one of these electrons is missing. Let's just make it that one, just for fun. And so one of these electrons would be missing. It's only got 3 electrons in the entire thing. So now the bond order is going to be 2 electrons in bonds minus 1 electron in antibonds. And now I've got a bond order of 1/2. So if I were to make, and this is now helium plus, and so this is helium-2+. If I were to make helium-2+, I could make it. There would be a weak bond connecting the two. This is definitely not something you can see with Lewis structures. You can't do 1.5 bond or half a bond with the Lewis structure. Not very easily, at least. Lewis structures is all about satisfying octets, and you can't do that here. So that is helium plus. Now what about lithium-2? I think it's on the next page. So lithium, here's helium. All right, no big surprise. Not stable doesn't exist, but so here's lithium. So what is the difference between lithium and helium? Well, lithium has the 2s orbital as well. And so the 1s orbitals will overlap. Do that. 2s orbitals will overlap. And you don't have to worry about how to do this yourself, because this is a little bit more advanced. Just want to make sure that this makes sense to you. Generally, orbitals of similar energies will interact only. If they're 2 different energies, they won't interact. So that's why this interacts with that, and that interacts with that. But notice they both make bonding and antibonding. I've got 1, 2, 3, 4 atomic orbitals. Those 4 atomic orbitals mix together to make 4, 1, 2, 3, 4 molecular orbitals. So that works. But anyway, 3 electrons each, 6 electrons total. 1, 2, 3, 4, 5, 6. And you get a bond order of 1 if you calculate it. So 4 minus 2 divided by 2 gives you bond order 1. So this mythical lithium-2 molecule could exist. Now lithium is a metal. In real life, it will make a whole bunch of bonds, metallic type bonds, which we're going to examine next. But if you could make a dilithium molecule, yeah, it would work. Very Star Trek-y, but It's fake. Now normally we don't really care about the core electrons. You can just focus on the valence electrons. So this was kind of overkill here. You can just focus on that part, and it'll work. All right, so let's, one more thing to introduce before we get to the metal stuff. What happens when you involve p orbitals? Same thing. You can make molecular orbitals from atomic p orbitals as well. But remember, p orbitals come in sets of 3. Every atom, like carbon, nitrogen, oxygen, fluorine, they all have 3 sets of p orbitals. One set goes up and down, the other one goes left and right, the third one goes in and out. Those are the 3 directions. Well, 2 of those orbitals on each oxygen, for instance, if I have oxygen, will point directly at each other, like that, and do an end-to-end overlap, a sigma bond. And of course, they'll do the sigma antibond same way. But then there are 2 sets of p orbitals that are parallel to each other, like that. And if they're oriented side to side like this, they will do a side-to-side overlap, which is called a pi bond. We did learn that in 221. And of course, they can make the pi antibond as well. But there's 2 sets, so the ones that go up and down, and those are the ones that go in and out. So there's going to be 2 sets of pi bond, pi antibond. There'll be another one. And this is the kind of pattern you'll get. So here you go. For oxygen, for instance, you'll have the 2s and the 2p. Here's the oxygen 2s and 2p for another oxygen atom. When they mix together, the 2s's will overlap, make sigma bond, sigma antibond, and the p's will overlap, making a sigma bond, sigma antibond, and 2 pi's, 2 pi bonds, 2 pi antibonds. Big, a lot there, okay? Don't worry about memorizing this. I will provide this outline to you if you ever need it. But what you do need to be able to do is fill it with electrons if you ever need to, and calculate a bond order. So for oxygen, fluorine, and neon, it looks like this. Pretty normal pattern. For boron, carbon, and nitrogen, it almost is the same, except these are swapped. So the sigma is higher than the pi. That's the only difference. To go back, see? Here the sigma is lower than the pi. There's that. That's the only difference. And the only reason I'm showing this to you is you don't have to memorize it. When you do any kind of homework and you have to fill electrons, and is it paramagnetic, is it diamagnetic, it'll matter which one you use. So make sure you understand which one you need to use. But there you go. That's what they look like. So what do we do with it? Well, let's say we wanted to understand which of these weird things is the most stable. How would I do that? Well, I'm going to use MO theory to find out which is the most stable. And the last class had a little trouble with this, so let's do this on the board. Well, what does most stable mean? Most stable means strongest bond. So we're looking for the one with the highest bond order. All right, well, let's start with, instead of bond order, let's just start with how many electrons each one of these can contribute. So for C2, 2 plus, how many total valence electrons will that contribute? Close. So carbon has 4 valence electrons. Yeah, so 2 carbons is 8, but then a +2 charge means you're missing 2 electrons. So 6 total electrons. All right. If I go down the line, N2, 2 plus, how many electrons? Still 8. Well, not still, but 8. So each nitrogen's 5 valence electrons. Yeah, not total. Oh yeah, I see what you meant. Not total, just valence. So 5 valence electrons each. So that's 10, but minus 2, because it's a +2, so 8. B2? 6, yep. C2, 2 minus? That's 10 electrons, yeah. 4 each, plus an extra 2 from the -2 charge. And then last, B2, 2 plus? There's 4. Okay. So let's figure out bond order now. And it's not as simple as knowing the number of valence electrons. We actually have to fill those valence electrons into this orbital diagram. So I'm going to draw this over here. And we're going to just do the center. That's all that matters. We don't care about the side. The side is this side here, and this side here is what the atomic orbitals originally look like. We don't care about that right now. We care about what the molecular orbitals look like. So here's your sigma from your 2s. Here's your sigma star from your 2s. Here is your pi from your 2p's. Here's your sigma from your 2p's. Here's your pi star from your 2p's. And here is your sigma star from your 2p's. So we'll fill these with electrons. Let's start with the highest number of electrons, C22 minus, which has 10 electrons. So 1, 2, 3, 4, 5, 6. Remember, 1 electron in each degenerate orbital before you pair them up. Degenerate meaning same energy. So 2, 4, 6, 7, 8, 9, 10. And then we'll calculate bond order. So bond order is number of electrons in bonding orbitals. That's a bonding orbital. There's no star in it. That's not. That's an anti-bonding. But that's a bonding orbital. That's a bonding orbital. So 2, 4, 6, 8 electrons in bonding orbitals. 2 electrons in anti-bonding orbitals. These are empty, so there's none there. But 2 electrons in anti-bonding orbitals divided by 2, you get 3. So for this 10 electron species, this has a bond order of 3. Pretty strong bond. If I go to the next step down, nitrogen, or N22+, I should say, it's got 8 electrons only, so these 2 are not there. And now the difference is the bond order is going to be 6 minus 2 over 2. Double bond. Maybe I did that fast, but I did that really fast, sorry. So again, 2 electrons in a bond, 2 more, so 6 total electrons in bonding orbitals, minus 2 electrons in antibonding orbitals. That's 4 over 2 is 2. When I get to number 6, or B2 or C22+, these only have 6 total electrons. 2, 4, 5, 6. That's what 2 of those things look like. So the only thing different is there's only 4 electrons in bonding orbitals. Still 2 electrons in antibonding orbitals. The bond order is going to be 1. This one's going to be 1, and that one's going to be 1. And then last but not least, B22+. That's gone, and that's gone. It's only got 4 electrons total. And what's going to happen to the bond order? 0. No bond. All right, 2 borons with a +2 charge is not going to make a bond. Now, don't make a mistake. So the answer is this one. That's got the strongest bond. That is the most stable, which is weird. You'd think, oh, something with this charge is stable. It is. It's got the strongest bond. Don't make the mistake of thinking more electrons is better, though. Just because it has 10 electrons the most. What if I had something that had 12 electrons? What would happen? So 12 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If something had 12 electrons, notice those 11th and 12th electrons are starting to go into antibonding orbitals again. That would start to weaken the bond. And so the bond order would start dropping again after going up. Now it's dropping again. So there's a, for every MO diagram, there's going to be an ideal number of electrons to get the strongest bond. All right, so this is, you can see the power of these things. They are exceedingly complicated sometimes to look at, but they are very, very powerful. We're not going to focus on this right now, but one of the questions was, well, how do we explain how a molecule will absorb energy? So when it absorbs light, absorbs red light and looks blue. How does it do that? Well, because we can calculate the different energies between these things. So when we look at atomic orbitals, for instance, hydrogen, the transition of So we excite hydrogen and it emits these 4 colors of light. It's a 3 to 2, 4 to 2, 5 to 2 transition, right? We learned all that. Well, these have transitions too. An electron can go from here to here and absorb whatever this energy gap is. And that could be a visible light, could be ultraviolet, could be something. But all of these calculations, all of these things are used to kind of understand the absorbance spectra, all that. So there's a lot going on here, which is why I keep saying that this is like an advanced class if you want to really understand them. You have to learn new kinds of math even. We have to learn a math called group theory, which is a math about symmetry and understanding how 3-dimensional shapes can transform and remain the same. And for somehow those transformations will translate into chemistry. It's weird. It's really weird stuff. Anyway, this is a taste, which is probably not to most people's liking, which I understand. Even me, I'm like, this is not the best.
So question, you said that we're going to need to know which diagram to use. Are we going to have multiple options?
So for the homework, you might need to look up the particular, this one or that one. But for a quiz or an exam, I will just give you an outline. And if you need an MO diagram to fill out, I'll just show you, here, this is the outline of it. Put the right number of electrons, tell me the bond order, things like that. That's it. But there's only this one and the other one for the more complicated ones. We're not going to do anything crazier than that. Yeah?
Just curious, with bond order, how directly correlated is it with bond strength?
Oh, I mean, it's not proportional in the sense that if you make a double bond is not triple the strength of a well, when you go from a single to a double bond, it's quite a bit stronger. But when you go from a double to a triple bond, it's not, the same jump from a single to double.
So it's not like a linear.
It's not a linear, yeah. It's not linear, no. But they do get stronger, yeah.
So you said that when the bond order value increases, then the strength of the bond is increased?
Yes. Yeah. It's not a linear relationship, but it does go up. Yeah. Okay. So the big takeaways, if anything, you can get from what I just went over is first, that splitting of bonding to antibonding, it depends on how good the atomic orbitals overlap. If 2 atoms can get really close together and really overlap their atomic orbitals well, then you'll end up with molecular orbitals, a bonding one and an antibonding one, that have a big gap between them. If the overlap is not good, then the antibonding and bonding MOs will have a smaller gap between them, which we can't really see here. But there's a gap between the bonding and antibonding, and the bonding and antibonding. So the size of that gap depends on how well the overlap is. The last thing is the law of conservation of orbitals. This is the bigger one. You get the same number of MOs as atomic orbitals you start with. Now, this is where we get the 24C finally. So, what happens when we have more than 2 atoms? And we're going to start really, really simple, because when you start including tons of different orbitals, it gets really complicated. But let's start with a very simple s orbital on every atom. And what you're looking at here is pretend, instead of having an atom on this side and an atom on that side with the atomic orbitals separate, we're putting them together. So here, these 2 atoms each have an s orbital with 1 electron in it. And so what you're seeing here are the 2 s orbitals, same energy, with their electrons added up together. And when those 2 atomic orbitals mix together, what happens to them? They make a bonding MO and an antibonding MO. They split. The electrons will go into the lowest energy orbital possible, the bonding. That's what happens when you have 2 atoms. Well, let's add a 3rd atom. What happens if I add a 3rd atom? Well, this is what happens. You get a pattern like this. 3 atomic orbitals will make 3 molecular orbitals. These three atoms each have 1 electron each, so 3 electrons. And these MOs still only hold 2 electrons. So 2 of them will go down here, the third one will go up here. And the MOs tend to be symmetrically distributed between 2 extremes. That's the pattern we're going to see. So 3 atomic orbitals make 3 molecular orbitals. FYI, this is definitely bonding. That is definitely anti-bonding. We call this one a non-bonding. You don't have to know that name, but in case you wanted to know what it is. It's not anti, it's not bonding, it's just nothing. It doesn't do anything. So if I put 4 atoms together, what happens? I get these atoms that have 4 atomic orbitals each will make 4 molecular orbitals. And again, they will be symmetrically spread out between the 2 extremes. And 4 electrons will be occupying the lowest energy MOs possible. Notice, they're only occupying the lower half, just because of how many there are. So if I kind of bring this pattern to an extreme, not 5, not 6, but let's say I've got millions of atoms, what would happen? Well, I would still have my extremes of where the lowest bonding MO is and where the highest anti-bonding MO is. But since I'd have millions of atoms, I'd have with millions of atomic orbitals. I would be making millions of molecular orbitals. But now, there's just so many that I can't draw every one of them individually. They kind of just smear together. And we call this a band. So a band is just a bunch of MOs, molecular orbitals, too close in energy to really see individually. And they're just all smeared together. The pattern of electrons is still the same. I've got a million atoms, so I'm going to have a million electrons. And they will fill, because each MO holds 2 electrons, they will fill the lower half of my band. So this is kind of the picture we're going to see from now on. We're going to see these bands that are made up of many, many, many MOs kind of stacked on each other. Okay? So same pattern again. I start with 1 atom with the 1s orbital. If I make it 2 atoms, I'm going to have bonding and antibonding. If I've got 4 atoms, I get this, and until I get many, many, many atoms, which will make this band. Now, the filled part of the band and the empty part of the band, they have a name. The filled part is called the valence band. Valence, you can remember as, hey, that's where the valence electrons go. They occupy the valence band. The empty band has a very, very appropriate name. It's called the conduction band. We know why it's called the conduction band. Because it's what causes conduction to happen. So let's think about why a metal conducts. What is the requirement for something to conduct electricity? We've mentioned this before. What has to happen inside for conduction to happen? So moving charges. As long as they can have charges moving inside, that's conduction. So a moving charge is current. And in a metal case, the moving charges are electrons. So if electrons are freely moving, able to move around inside your material, it can conduct electricity. So how does this explain that? Well, these MOs are filled, right? Every single MO, all of the atoms have those lower MOs filled up. So an electron from one atom cannot go to any other MO here on a neighboring atom, right? But these are empty. So an electron right here on one atom could jump to a nearby atom that has an empty MO. And how much energy would that electron need to have in order to get right across this gap? Nothing, right? It's right there already, almost. So the fact that the empty band, the conduction band, is right next to the valence band means that these electrons can just move around very easily. That's what makes a metal conductive. Okay. nearby bands where there is no energy required to move up. Like, you know, this right here, there's an empty space for an electron, right? Well, let's imagine these are empty. Electrons can get in here, but how do I get this electron to here? I've got to give it a big amount of energy, whatever this gap is. But here there's no gap, right? No gap at all. So electrons are free to move up there and start moving around. That's what makes things conductive. So let's look at another example, lithium. So lithium is a metal. Normally it'll be a bunch of lithiums, but let's just look at a tiny piece of lithium, 6 lithium atoms. And this exercise is going to help us kind of understand how we're going to talk about bands. Let's put it that way. So if I talk about lithium-6, what is the electron configuration of lithium, first of all? Or the valence electron configuration? 2s1, right? Okay. Now, does lithium have p orbitals? Anything in row 2 does have p orbitals. They're not being used. So that's a little trick question, but they're not being used. So even though we've never done this before, let's say that this is part of the electron configuration, but there's no electrons in it. So let's put a 0 on it. Just to make things clear. So the lithium does have p orbitals, but they're not being used. Okay. So how many MOs will form if I have 6 lithium atoms? Yeah.
I was going to say, is it the same for the D? Like,
It is the same for the D, but if you're in row 3. Yes. Yeah, so when we did the expanded octet, like when we broke the octet rule for some of those Lewis structures, the reason we could do that is because everything in row 3 had empty d orbitals. And that's how we broke the octet rule for those elements. Anyway, so if I have 6 lithium atoms, how many MOs will form with those valence atomic orbitals? More than 6. So how many total, so 1 lithium, how many valence orbitals are in 1 lithium? We kind of just wrote it down here. There's a 2s. And what about the 2p? How many orbitals are there in the 2p's? They come in sets of 3, right? The 2px, 2py, 2pz, or m sub l 0, m sub l 1, m sub l minus, whatever. So 4 atomic orbitals, 4 valence atomic orbitals. Each lithium has 4 atomic orbitals. And if there's 6 lithiums, there's going to be 24 total atomic orbitals. And the law of conservation of orbitals is those 24 atomic orbitals will make 24 molecular orbitals. All right, we can kind of look at them as a band if we wanted even. So, you know, you've got the lowest one, bonding, you've got the highest one, the antibonding, and then there's going to be, I don't know, 24. So 1, 2, 3, 4, 5, 6, 7, 8, lots of them. Should be 24. 24 lines. All right, that's the, you know, it's a really crude MO diagram, but that's kind of how we're going to be thinking from now on. Okay, we're going to simplify things. So how many of them will be bonding? How many of them will be antibonding? Exactly. If I'm going to make 24 MOs, half of them will be bonding, half of them will be antibonding. So 12 and 12. And then what is the capacity of all of those MOs?
48. 2 electrons.
Yeah, 2 electrons each. So 48 total electrons. And now what is the capacity? Oh, there it is. Sorry. I did it again. So what is the capacity that is filled with electrons? Each lithium comes with 1 valence electron. So 6 lithiums, 6 electrons total. So 6 electrons out of 48 spaces for them means that they'll be 1/8 filled. So if I were to kind of show you, well, where is the valence band, where is the conduction band? I break this up into 8, and so this is like 1/8. So 1/8 of the whole. This is our, not valence, this is our valence band. This is the band that is filled with electrons. This is the conduction band. This is our band that is empty and ready for electrons to bump up into and do conduction for us. So this is the very beginning of band theory. Okay, we're going to do a little bit more into this, but you know, if you're at all interested in material science, in electrical engineering, you'll do this a lot. You'll study this stuff in terms of band theory, because you can do crazy stuff with band theory. You can do doping. You can do not doping like sports, but like you add weird atoms inside the metals which will add electrons, which will take away electrons, which will influence how the conduction works. But we'll get to some of that. There you go. So that's the picture. All right. Now, gets complicated, you know, so we don't have to get it perfect. Yes.
Just curious, so like on the previous slide, is it always the rule that half go to bonding and the other half to anti-bonding?
Yes, in a sense, yes. They are so you can see that there are varying degrees of antibonding, varying degrees of bonding. We're calling it bonding because they're lower in energy than the originals. So and this is actually hard to see because your S and your P's are somewhere here, your S and P's are somewhere here. So some of the bonding is lower and higher in energy than it's complicated. But in general, yeah, half of it's bonding, half of it's antibonding. If I were to show you a real band diagram for like something, even I would have trouble following it. They get quite complicated. But this is the basics. This is how we start to understand what they are. All right, so just to kind of emphasize what we're learning now, we're learning metallic bonding, okay? The electrons are loosely held. It really only happens in larger atoms. And because they're larger, they have poor orbital overlap. So remember what that does for our bonding versus antibonding. It keeps the gap between bonding and antibonding small. That's going to be important. We'll see why. But it causes delocalized bonding, meaning we don't really care exactly where the electrons are. They can be anywhere in the molecule, anywhere in the structure. And the bonding and antibonding orbitals, they tend to make this continuous band. So how does this differ from covalent bonding? If we try to do covalent bonding with these multiple atoms, like in diamond, for instance, what happens? Well, that only happens with smaller atoms generally. Higher electronegativity. They tend to then have tightly held electrons. The orbital overlap is much, much better. And so the bonds are stronger. And because of the good orbital overlap, the bonding-antibonding separation is a lot bigger. And what that'll do is that tends to cause there to be a separation between bands. You might have a band that's one size and another band that's another size, and there'll actually be a gap between them. And that's going to affect things like conductivity, you'll see. So going back to sodium, this is not the true band model of sodium. This is a simplified one. We're only showing the s orbitals, unlike the lithium picture we just saw. So if you just think about s orbitals, this is the conclusion. You get, bonding and antibonding. I don't really like this one. I'm going to skip this one real quick. But let me switch to the next slide deck. So like I said, I'm trying to go fast. Come on. Uh-oh. Crashed Windows 11. It's okay. I don't need to. There we go. It came back. Crashed Explorer. Okay. So, there we go. So this is what I was talking about. Now, it's a little bit weird to think of a covalent compound like the ones we just saw, H2 and N2, having bands. But you can think of them as having bands too. The difference between a metal and something that is going to be more covalent-like, the gap between the conduction band and the valence band is going to be really big. So what does that mean? Well, again, what does it take for this to be conductive? We needed electrons to be very easily able to get to the conduction band. These electrons can't get to the conduction band very easily. If you want to get to the conduction band, you have to bombard that molecule with a ton of energy to get the electron to jump up across this gap into here, which doesn't really happen. Okay, the gap in this case is going to be so large that it doesn't really happen. All right, we did this. All right, and we talked about this. So here's where we start Chem Activity 24C. Finally, we're going to talk about bands. And so again, the low band is the valence band for group 4 elements. So we're going to focus only on group 4 because that's what we warned you, we're going to focus on one thing only to make things simple. And because we're focusing on group 4, it makes our band very predictable. The bands are always going to be half filled. Or I shouldn't say half filled. Let's put it this way. The valence band is going to be full. The conduction band is always going to be empty because it's group 4. So that'll make things simple. So there we go. That's what a group 4 band diagram looks like. The valence band, which is full of electrons. You have your conduction band, which is empty. The valence band is made entirely of bonding MOs. The conduction band is made entirely of anti-bonding molecular orbitals. This is how it works for group 4. Makes it easier. And this gap between them, here's a new term, is called the band gap. We label it with this capital E for energy, lower subscript G, that's a very common symbol for band gap. And remember, this is quantum mechanics. There is no orbital there for an electron to go. So if I want an electron, if I want this material to absorb energy, it has to be greater than the band gap. Because if I'm going to make this molecule or this substance absorb energy, I've got to be able to have an electron jump up to an empty MO, an empty orbital. Same kind of picture. This is how, this is where the electrons come from. So this is one atom, this is one atom. But imagine millions of atoms doing the same thing, and you make these two bands. Okay.
Did you move on to the next set of slides?
I did.
Okay.
Sorry.
You're fine.
All right. So we're, like I said, we're focusing on group 4. That's carbon, silicon, germanium, tin. And remember that they all have the diamond structure. Some form of tin does have diamond structure, not all forms of tin does. And they all have a similar looking band gap model. Full valence band, empty conduction band. But what's going to be different between them is that band gap. So if it's a metal, there's going to be little to no band gap present. If it's an insulator, and that's just another way of describing a nonmetal, which is not conductive, it will have a very large band gap. But there's going to be this intermediate range, where the band gap is there, but not very big, in which we can call it a semiconductor. It's not a conductor, but it can become a conductor through adding energy. And that's how silicon works. Silicon does not conduct out of the box, but if you give it energy, you can heat it up, it'll become conductive all of a sudden. And that's because when you heat it up, you're giving these electrons enough energy to bridge this gap, and suddenly now they can move around. Okay. Most band gap energies, since this is a cross-disciplinary thing, we use, instead of joules, which is the SI unit for energy, you'll often see electron volts. So we're going to see electron volts a lot, but we need to be able to convert between electron volts and joules. So be sure you know how to do it. There's the conversion. You don't have to memorize it. I'll give it to you, but make sure you know how to do that. And for actual values, if it's a semiconductor, it's going to have a small band gap, which is going to be less than 3 electron volts. So silicon and germanium fall in this range. If it's an insulator, it's going to have a band gap that's greater than 3 electron volts. So diamond is an insulator. Ceramics are insulators. Okay, things like that. And why do we need to know that? Well, let's go back to 221. 221, we studied giving in a hydrogen atom some energy, and then watch the electron relax back to a lower energy level, and it emits a photon. Well, we're going to do the same thing with these group 4 materials. We're going to give them energy. We're going to make the electron jump across the gap to the conduction band, and then we're going to let it relax. We're going to let the electron drop back down, and when the electron drops back down, it'll emit a photon. And we can calculate the energy of that photon. So we can, if we know the wavelength of that photon, we can calculate the energy of the photon. And the energy of that photon will be exactly the band gap energy for that material, because that's the energy it crossed. So notice that in order to calculate wavelength from energy, we need Planck's constant. Planck's constant has joules in it. So you need a joule energy value to plug in here. But most of the time your band gap is going to be in electron volts, so that's where the conversion comes in. Okay? So let's try this. If silicon has a band gap energy of 1.1 electron volts, what wavelength of light is emitted when an electron drops from the conduction band back to the valence band? So just a visual of this, I've got my valence band, and I've got my conduction band, and the valence band is full of electrons. Right, these are all electrons in here, but it's excited. This piece of silicon has been excited already, meaning there's a couple or maybe one electron that's already in the conduction band. It's mostly empty except for like a couple of electrons. Well, this electron is going to drop back down, and when it drops back down, it relaxes. It's going to release light. Right, HV, that's our symbol for light. What is the wavelength of that light? Well, to know that, we need to know what the band gap is. What is the difference in energy between these two bands? So I've got it, it's 1.1 electron volt. So let's convert that to joules. And 1 electron volt is 1.602 times 10 to the minus 19 joules. And calculators as well. Uh, 1.1 times 1.602 e to the minus 19 is 1.76 times 10 to the minus 19 joules. It should be 2 safe things, but I'll just keep it for 3 for now. Now let's use, this is the energy of the band gap. It'll be the energy of the photon that is emitted. And so if the energy of the photon is that, the energy of a photon is equal to Planck's constant times the speed of light divided by the wavelength. I'm just going to rearrange this. I'm going to put wavelength up here, energy of the photon down here. You could plug things in first if you want. So Planck's constant is 6.626. 6.626 times 10 to the minus 34 joule seconds. C is the speed of light, 3.00 times 10 to the 8 meters per second. And so the seconds will cancel. Energy is going to be 1.76 times 10 to the minus 19 joules. And that's when we converted the joules. So this joule and this joule will cancel. And we're left with meters. 6.66 to the minus 34. 3 to the 8 divided by that original number. I get 1.1 1 times 10 to the minus 6 meters. So I ran into 2 sig figs. But this is in meters. Most times wavelength of light we like nanometers so that we can see if it's a visible light or not. So let's convert this to nanometers. 1 nanometer is 10 to the minus 9 meters. So this becomes 1,100 nanometers. Is that visible? Now, if you don't remember, visible light is 350, 400 to 750, 800, something like that. So this is definitely not visible. You know what range it's in? Red is 800. So this is beyond red. This would be called infrared. So this is infrared light. So when silicon emits light from after being excited, it will emit an IR photon. So why does that matter to us? Well, maybe not silicon, but it's similar. How do you think our night vision goggles work? So night vision goggles work by seeing infrared light. So it's silicon or something else that is like silicon inside the sensor. Infrared light hits it. It causes an electron to jump up here. Suddenly it's conductive, and we can tell that through electronics. And we can say, hey, it's reacting to infrared light, and that's how these things see in the dark. They react to infrared light. This is also the start of how solar cells work. How do we capture sunlight energy? It's through things like this. So we're going to get to all that in this section eventually. Okay? All right, so band gap is extremely important in modern civilization. It's really important. We'll eventually get to LEDs and all that stuff too. All right. So, now, Model 5 of Chemactivity 24C is where we'll actually start using the workbook. So what we're going to do is examine these different group 4 materials and look at kind of their crystal structures, which are all diamond-like, right? But they have different unit cell sizes. Their band gaps, these are the wavelengths of light that is emitted when the band gap is excited and then relaxed. And so let's just kind of go over the questions here. So I don't know the exact page, but it's somewhere in the middle of 24C. Start with question CTQ 35. And they're not hard questions. They're just questions that kind of organizing what you know already and kind of making sense of some of the things we've learned and what band gap is and how it's related to all these other things we've already learned.
So the visible region of the spectrum ranges from, is this where you want us to start?
Yes, right there. So that's page 51. Thank you. Brain overload yet? We'll slow down. Thanks, class. I'm going to make sure we get through as much of this as possible. So we get the homework done.
So we just need to do the calculations with, they've given us these figures, which is what we were figuring out. Here,
Yeah, so we
sort of.
just did that calculation
Yeah.
from that, yeah.
Mhm. Okay,
Yeah, I don't think these questions make you do any calculations though.
got it. Oh, because it already gave it to us.
Yeah.
Brain overload.
yeah. Well, this is why we're stopping, pausing, let you guys think a little bit, and
Yeah.
The MO theory stuff is a little heavy, that's for sure. area, the weaker they get. And the bond length is going to be proportional to how big the atoms are. The bigger the atoms, the longer the bond they get. The bond strength, it's going to decrease.
Okay, so as the gap gets smaller, also decreases strength.
Yeah, I mean, it goes back to the idea that the more orbital overlap there is, the bigger the difference between the
Okay.
bond and antibonding orbitals are, and so that's directly related to how big the band gap is.
Okay.
So the less overlap there is, the weaker the bond is going to be, but the smaller that band gap is.
That's like metals or so.
Yeah, metals have weak bonds, but because of that, they have no band gap and they're conductive and yeah. They can make tons of bonds with neighboring atoms. Electrons are not localized. They're not forced to be between two atoms.
Wander.
Yep.
And that's like, tin and uranium are more common.
Oh yeah, yeah. Well, tin is a metal. Germanium is a semi-metal, but yeah.
Okay, that makes sense.
Sounds alright. I get it like this.
All right. All right. So hopefully there's a few light bulb moments. Where you're like, oh yeah, this makes sense. Oh, I didn't load it. Let me get my thing loaded. There we are. Does any of them emit visible light?
No.
No. So diamond is in ultraviolet, and after that they become infrared again. I think tin is still infrared, even though it's really large. But so what region does SI emit? Infrared. How does the bond length vary as you go down a group? Bond length increases. As the atoms get bigger, the bonds have to be longer. We measure from the center to center, so the bigger atoms make longer bonds. The bond strength does the opposite. It goes down, and it has to do with overlap of orbitals. The smaller the atoms are, the better the overlap of the orbitals can be, and so the stronger the bond can be. If the orbitals are not overlapping much, then it's going to have a weak bond. But at the same time, the band gap, the larger the band gap, the stronger how is band gap related to bond length? the longer the bond, the smaller the band gap. And it's orbital overlap. The longer the bond, the less orbital overlap there is. And remember what orbital overlap does. The more orbital overlap, the bigger the difference between the bonding MO and the anti-bonding MO. That's the band gap. So, yeah, the longer the bond, the smaller the band gap. And so the stronger the bond, the greater the band gap. Carbon, diamond, has very strong bonds, but also has a large band gap. So how do we explain the conductivities? Yeah.
Or just to make sure I understood that right, the conduction band then represents electrons getting kind of launched into anti-bonding orbitals?
Yeah.
Okay.
Yeah. So they have to be, the electrons have to be in for group 4, have to be in that anti-bonding MOs in order to conduct. Yeah.
Okay, thank you.
It's not all of them though, it just has to be a few of them. That's it. And you know, I guess you could talk about what if you put a giant current through metal, what happens? That's beyond what I know. So maybe something happens. There's some kind of breakdown, current. I don't know.
Sure does melt eventually.
That's electrical stuff. Okay, so let's expand on this topic, and we're going to go. So we answered this already. Bond strength causes a band gap to increase. So we're going to switch to, there we go, isoelectronic solids. So before we did this section, we talked about isoelectronic materials. We took germanium, for instance, took half of the germanium atoms and replaced them with gallium, which is 1 to the left of germanium, so 1 fewer valence electron. And then the other half of the germaniums, we replaced them with arsenic, 1 to the right. So 1 more electron than germanium has. So 3 valence electrons and 5 valence electrons, averaging out to 4 valence electrons still. So they're isoelectronic because they're still on average 4 valence electrons. So what happens when we look at materials made with isoelectronic solids to group 4? What happens to band gap and all that stuff? So next set of questions, 42 to 45. Just kind of internalize it to make sure you understand what's happening. So these all have diamond crystal structure or zinc blend, if you want to be more specific and accurate. So the boundary between semiconductor and insulator is about 3 electron volts. So 2 is not, it's significant, but it's still semiconductor. I think the most interesting one up there is the copper bromine compound, which we would think of as, in introchem, metal non-metal is what? Ionic. Yet it's still within the region of semiconductor, which is weird. But so normally we think of it as a salt, an ionic compound, but it can act like a semiconductor under certain conditions. We'll get to those later.
Sure, something like a diode, would that be similar to copper bromide?
So diodes, honestly, all I know about diodes is that they allow current to flow in one direction. I don't know what they're made of. I forgot. Actually, actually I do know. They are essentially the same as LEDs. They just don't emit light. Because LEDs are diode light. They only emit. I have to go and look. I don't know what material are best for diodes, but maybe it's that.
Okay, fair enough.
I'd have to see.
So, how does the integration go? I mean, I was saying that I would think it would go down.
Well, so the delta E is the difference in electronegativity between the
Oh, it
two
is bigger.
things.
Yeah.
So yeah, this left one is smaller, the bigger one is bigger. The difference is okay. I think we had enough time to kind of look over it. So what we're doing here is just reinforcing this idea of isoelectronic materials. This is just a proof that a gallium, which has 3 electrons, and an arsenic, which has 5, on average, will have 4 electrons. Right? So that's what makes it isoelectronic. So down here, do any of these emit light in the visible region?
Yes, the last two.
Yeah, 460, 430, that's pretty blue. Does bond length vary significantly? No, they're almost the same. And they're all from row 4, so you know that's not unreasonable. The sizes aren't changing. If you're replacing half with a slightly smaller and half with a slightly bigger atom, on average it's still about the same size. The crystals are going to be about the same. So no. So the point here is we're not changing the unit cell size. We're not changing the bond lengths too much. So what else is affecting the band gap? Well, how about difference in electronegativity? What's happening to that?
Increases as it goes down.
Yeah, the difference in electronegativity. So we're looking at, so in this case, 2 germaniums. There is no difference between the electronegativities of germanium, 0. But gallium and arsenic, gallium is going to be a slightly lower electronegativity. Arsenic is going to be a slightly higher electronegativity. So the difference is small, but it's growing. And now zinc and selenium versus copper and bromine, the difference in electronegativity is getting bigger and bigger and bigger. And notice what's happening to the band gap. As your difference in electronegativity is growing, the band gap is growing. Now, what other property can we talk about when we're talking about difference in electronegativity? How would we describe these materials? Are they getting more and more what? Close. Ionic. As your ionic character increases, that's the difference in electronegativity, the band gap is going to increase. As things become more ionic-like, yeah, they will have a larger and larger band gap. So remember what ionic and covalent do. They localize your electrons. So as you localize your electrons more and more and more, the band gap is going to increase. So we're going to cover a lot of this in the lab, and which is going to be not next week, the week after, but we'll see. All right. So what is the relation? I think I skipped the question. Hold on. Oh, we answered that. Okay. So what is the relationship between delta change in electronegativity and band gap? As one increases, the other increases. Now, here's kind of well, not the goal, but like, you know, the stuff we've seen so far is very restricted, very limited. So what can we do to kind of free ourselves from like the restrictions of what the periodic table tells us? So let's talk about a solid solution. And we've already looked at solid solutions. That's what lab 1 was about. We made alloys. An alloy is a solid solution. It's a mixture of metals. So if I do a solid solution with silicon and germanium, for instance, I could make any ratio of silicon and germanium. All right? We're not talking about a formula where you have to have one atom or a certain number of atoms in a molecule. We're talking about a giant crystalline thing, metal or whatever, that has so many silicons and so many germaniums. You could have 50-50, half-half. Half silicon, half germanium. But you could have any proportion. that doesn't matter. We're talking about a mixture here. Mixtures, you're not limited to specific ratios like molecules are. So you could do 20% silicon, 80% germanium. You could do any ratio. And we use the decimal form for the subscript here of the percentage. So 20% is 0.20 or 0.2. And in general, that formula for a solid solution would be written as SiX germanium 1 minus x. Plug in anything you want for x, 0.3, and this would have to be 1 minus 0.3, 0.7 then. Okay, that's the way it works. So you could make any ratio, and what that'll do is let you tune the band gap. So why? Well, germanium has a band gap of 0.66. Silicon has a band gap of 1.1. Because of that, the photon emitted from silicon is this, the photon emitted from germanium is this. What if you wanted this thing, this new material to absorb right in between? Well, I could do 50-50 silicon and germanium and try to make the band gap be somewhere in the middle. That's what a solid solution is going to do for me. So you could have any of these, and they would all have slightly different properties because of the amount of silicon or the amount of germanium in them. Remember, this is not a molecule. It doesn't have to be, it's not an ionic compound where you have to have perfect, the sodiums are here, the chlorides are here. These are just neutral atoms. They're just mixed in as random as they can be, evenly distributed, but it doesn't have to be perfect. That's why it looks like this. So this is pure germanium, that's pure silicon, and you can have anything in between. Somebody was going to ask a question? No? Okay. So, why would we do that? Again, I showed you the germanium silicon example, but what about LEDs? We'll get into that, but we make different color LEDs based on the band gap. That's going to affect the color of your LED. So it just so happens that a gallium arsenide LED has a band gap that is such that it emits red light. So the gap is tuned to whatever the electron volt is, that when I do my calculation over here, the value of the wavelength is going to be a red color wavelength. If I use gallium phosphide, it's going to be green. If I use gallium nitride, it's going to be blue. So how do I get yellow? How do I get orange? How do I get turquoise colors? How do I get any color beyond these three? Solid solutions is going to be the answer. I'm going to do a mixture of gallium with arsenic and maybe phosphorus too. But I have to be careful how much I use, because again, the goal is to keep this average number of electrons as 4. We need to keep it the same crystal structure, diamond or zinc blend, whatever you want to call it. So we need to make sure we have the right ratio of elements in there. So for instance, with these isoelectronic materials, remember how it worked. We took germanium, which had 4 valence electrons. We took half of the germaniums, replaced it with gallium, and the other half we replaced it with, for instance, arsenic. Well, now half of them are still gallium, but the other half is a mixture of phosphorus and arsenic. Both of them are 5 valence electrons, and they add up to 1, just like gallium is. Gallium is 1, this side is overall 1, 1-in-1 ratio. So we have to be careful that our ratios are the right ratios so that we keep our average number of 4 valence electrons, we keep our perfect band gap in our diamond crystal structure. Okay? So here's like kind of the formula. I don't know if we have time to do this today. But here's the generic kind of formula for a gallium with phosphorus and arsenic. I could use any ratio of phosphorus, and then I would have to figure out how much arsenic I could use as a result. You know what? Let's stop here. I think you guys are like great. So, you know, we'll get into this. We'll get into, I think that's it actually. We'll get into this and then we'll talk about LEDs a little bit more specifically next week, or not next week, Thursday, after our quiz. I'll reveal exactly what we're gonna have on our exam. We'll probably not have the LED stuff, but we may have some of the band camp stuff. Maybe, we'll see.
And when's the exam again?
Next week, Thursday.
Okay.
And next week, we do not have lecture on Tuesday, so, yeah, this
Do we have-
Thursday.
Do
Sorry?
you have like a practice test online?
Yeah, I'm gonna set that up for you, and I'll reveal it on Thursday.
Okay.
Yes.
What's the quiz location?
So the quiz is probably gonna be, it's not probably, it's going to be just on 24A and B. So, crystal structure stuff, so the stuff that we did in lab, and, well, not the lab stuff, but, because that's more advanced, but the stuff that's in 24A and B. So that was our homework, zinc blend, diamond, crystal structure, and then I think 24A was the basic one, so FCC, BCC, simple cubic, packing efficiency, the equations I'll give you if you need them. So if you need the, oh, and then the density of material using crystal structure, that stuff, yeah.
And
Like
you-
you'll give us the volume and stuff, or?
I'll give you equations for calculating a side or a volume for a specific unit cell. You should still know the volume of a cube is length times width times height. That's on you, but, and I'll give you radius of a sphere, 4/3 pi r cubed, I'll give you that if you need it. You probably won't need it, because that's packing efficiency, so that's like extra credit. But know the order of packing efficiency, simple cubic is the weakest or smallest packing efficiency. FCC is the highest. Nearest neighbors, 12 for FCC, 8 for BCC, 6 for simple cubic. Tetrahedral holes, tetrahedral, yeah, everything to do with that. All right.